We're going to begin with a few introductory examples to prepare us for an entire unit dedicated to limits. So what we've talked about in the past, and if you've ever had any lessons on limits, you know that a limit is a number, a y value, an output, that is being approached as an x value is being approached from both sides. It is the value that it appears the function is going towards. It does not necessarily have to reach this value, but it has to be a clearly defined number in order for the limit to exist. So let's begin. Our first example here is asking us to find the limit as x approaches 1 of f of x. If f of x equals, alright, this over here is a little fancy bracket that we use whenever we're dealing with something called a piecewise function. Now, a piecewise function is something that you should be familiar with. Okay, this is breaking it up into pieces. It's saying, all right, y is equal to this set of outputs when the circumstances for x meet those criteria. All right, so it equals 3x minus 1. I'm sorry, 3 minus x. It equals 3 minus x, which is also y equals negative x plus 3. So I have a line with a slope of -1 and a y-intercept of 3. Here's the 3, down 1 over 1, down 1 over 1, down 1 over 1. Sure, we could graph that like middle school days. However, there seems to be this random open point in our graph that is a removable discontinuity. You may call this a hole. And that's because it says that y is equal to this line when x doesn't equal 1. So there's where x equals 1. If this were a dry erase board, you kind of just go wipe right over there and that point is erased. We draw a big open circle to indicate that that point is not there. Next, we also have that y is equal to 1. Well, that's pretty straightforward. A lot of the time, when you have y equal to 1 or 2 or any other constant, you might make a horizontal line. And here it would normally make a horizontal line. However, it only equals y. Y only equals 1 when x equals 1. Well, what does that mean? Well, it's the 0.11. That's all it is. Over 1 and up 1, and there's the point. Okay? Now, whether or not this point was here is not going to make a difference in your limit. As x approaches 1, when we approach 1, we're going to close in from the left and the right. You're coming in like this, okay? But you come in along any defined function. This is the only function here, and you can't worry about there being function anywhere else because it has to pass the vertical line test. You know there's nothing else. So you're coming in toward 1. You're getting closer and closer from both sides. Where does it look like the y value is headed? It doesn't matter where it goes. Where does it look like the y value is headed? And the answer is going to be 2. You can do this entire problem without graphing at all if you just know, if I'm approaching 1, I should probably just pay attention to everything except where the 1 is, okay? I know that this is where x equals 1, and this could be helpful in certain cases. However, in this case, in the case of the limit, it's not about where you get. It's not the destination, it's the journey, okay? So this over here would be different if we asked, what is the f of 1? What is the value of the function at the x value of 1? Well, in that case, when x equals 1, what does y equal? 1. That's different. That's evaluating a function. Evaluating a function, whereas what we were doing was taking a limit, okay? Or evaluating a limit. That is the limit. It is not the same thing, okay? Next example. The next example, use the graph to find the limit as x approaches -1 of f of x if f of x equals 1 over x plus 1. So in the function practice examples, we did a ton of examples like this, okay? We dealt with a ton of rational functions. And they're asking us when x approaches -1. Well, -1 is actually, of course, where my function's undefined. Limits love to ask you to approach a place that is undefined. -1 is undefined. It's an infinite discontinuity, okay? And that means we have a vertical asymptote. We've talked about that, right? Vertical asymptote at x equals, I'm a little cut off right there, see? At x equals -1. So when I approach this value, which I can do, I can approach it, well, I'm still approaching from both sides, and you don't have to get somewhere. We just saw that blue point didn't need to be there. We could still approach that open circle. So we could still approach the value of -1, the x value of -1. So we're going to close in on both sides. Now the issue here is you don't have a clearly defined number that we're approaching. As I approach -1, so I'm going to break this apart a little bit. The limit as x approaches -1 with this little plus sign means from the right of f of x Well, are we approaching a number? Oh, sorry, I'm cutting it off again. Are we approaching a number? Not at all. We're definitely just going up forever. So that means you're actually approaching infinity. Keep in mind, all right, infinity is essentially a fancier way of saying the limit does not exist because we're approaching infinity, all right? Now, what if I wanted to look at it from the other side? I'm coming this way now, okay? If I'm coming from this side, well, that's the limit. As x approaches, we're still approaching -1, but we're approaching it from the left. That's that little minus sign, so I'm going over one-sided limits right now. As I approach -1 from the left side, my graph clearly shows that I'm going down forever. That's negative infinity, which is another form of does not exist. So at the end of the day, what it really comes down to is that this limit does not exist, okay? Now, if both sides were pointing up and it was approaching positive infinity from both sides, we would write positive infinity as our answer. However, we are approaching two totally different directions, so we can't pinpoint what it's approaching. You would never put two answers. It operates like a function. You only get one answer to a limit, just like you only get one answer to the output of a function. Okay, you only get one solution. So the final answer for that one, to this particular question right here, is does not exist. Had it been one of these two questions, instead, the answer would be infinity, or the answer would be negative infinity, depending which side we were coming from. Do you need to graph to do a limit question like this? No. Does it make your life a lot easier and faster? Yes. Another reason, or another thing you could kind of do, is, we've talked about this, we went over it when we reviewed functions in the other video, but this is to the first power. If this is to the first power, when we graph polynomials, when we even deal with rational functions, it means that each branch along the asymptote caused by that factor, that each branch is going to be pointing in opposite directions. Just like as a factor in a polynomial, it meant that your graph went to the opposite side of the x-axis. All right, cuts through to the other side. So that's going to tell you that the branches on either side of the asymptote created by this factor will point in opposite directions. There's no need to fully graph. You should immediately know that if you're approaching -1 not from a side, you can immediately just put does not exist, because if one side's pointing down, the other side is pointing up, and that's it for that. All right, a couple more examples. Let's see what we got next. This next example, this to me again looks like another piecewise function, except the main difference is this time they don't actually supply us with the function. We have a clearly defined point right here that looks to be a break between a quadratic function and maybe a linear function. For good practice, it might not be a bad idea to try to write this function. So I'm going to take a few seconds to do that right now. The function is going to be piecewise. F of x equals, and we have this bracket over here. And hold on a sec. All right, so now I'd like to take a second to point out the two functions. So my dog wants to help. Right there is a parabolic quadratic function, and right there is a linear function. Now, the breaking point where one ends and the other one starts is going to be right there, when x is equal to 2. Okay, so that means if I just wanted to pick a color to assign each side, if this was a parabola, I'm not sure how the stretch would be, so let's see, over 1, up 1, looks pretty normal, over 1 and up 3, yeah. So it doesn't look like there's any stretch or compression. So in vertex form, that would be to the right 2, so x minus 2 squared, and then it's moved down 3 units, right? So we have that right there. Now again, where do we say the 1 ends? We said that it's going to go all the way until 2, right? So if it goes all the way until 2, that means it's good when x is less than 2. Now, because it meets the parabola or quadratic function, whatever you want to call it, because it ends where the other one starts, it makes it a little bit easier for us to not really have to decide which of the two graphs needs to be included. It really makes no difference. There's more than one right answer. So this one's linear. Now, instead of trying to work backwards and figure out your y-intercept, just put your line in almost like a vertex form as well. It looks like the slope is 1, up 1 over 1, up 1 over 1. Yeah, that's pretty good. So this slope is 1. It still moved to the right 2. It also moved down 3, and it exists when x is greater than 2. And I really, oh, sorry, I had been cutting off the equation. I was distracted because my dog is helping us do math. Okay, so we're right over here. So if I decide to make this point green, then that means it's included here. So when x is greater than or equal to 2. Now, did you need to write the function? No. But I feel like maybe seeing it get made might help us get better at graphing them, right? Because then you see it from both directions instead of always just trying to work in one direction. We kind of work it out in two different directions. Okay, so let's look at the limit. The limit is asking us, what is the y value being approached as x approaches 2? So if x is approaching 2 from the left, so let's do a one-sided limit. The limit as x approaches 2 from the left is that little minus sign of f of x. And I defined f of x right over here. Well, from the left side, you go along here, and now the pink is actually open, but it doesn't matter. What y value are you closing in on? -3. You could even just plug 2 in here. 2 minus 2 is 0, 0 squared is 0, minus 3 is -3. You could still do direct substitution because your parabola would get here, and then it would, scoop around, and that would still be the point where it would be had this not been cut off. So direct sub would still be helpful. All right, now the other side, what about the limit as x approaches 2 from the right of this function, f of x that I defined right over here, this piecewise. So from the right, x is greater than 2 when it's the right side of 2. So if I come this way, what y value are we approaching? And by the picture, again, it looks like -3. And by the equation, plug in 2 minus 2, 0 times 1, 0, minus 3, -3. So either way we look at it, you're approaching -3. The other deal is when you have a continuous function, which this one is, even though it appeared to be piecewise, when you have a continuous function, the limit you can just get by direct substitution, all right, by just evaluating the number you're approaching. You could just fill it right in to your function and you're good to go. Now if you were trying to plug in 2, if you had this function, for example, where would you plug it in? You'd plug it into the one where it equals 2. So when you're smooth, well, not smooth necessarily, but when you're continuous. Right now our definition of continuous is, we could draw it without picking up our pen or pencil. That definition will change shortly, but for right now, yes, you could think of it that way. Then you just plug in, and you would plug in to one piece, and you'll get your answer that way. All right? I have 3 examples up right now, and I want you to be able to tell me that which of these 3 examples are continuous on their entire domain. Does anybody know which of them are continuous on their entire domain? That's right, all 3. 1, 2, and 3. Okay? All 3 functions are continuous because there is no vertical asymptote or infinite discontinuity. We have no denominator with x in it, except maybe, sure, in that last one, there is a denominator with x in it, but there's no infinite discontinuity. Why not? In order to find your infinite discontinuity or your vertical asymptote, you find out when does your denominator equal 0. Well, algebraically, if you tried to figure out, all right, when does x squared plus 1 equal 0, and you tried solving for x squared equals -1. And if you didn't figure it out by now, you're out to lunch, okay? So come join us, please. X squared is always positive. It can never equal a negative number. There's clearly no solution to this part right over here, okay? So that's out. Graphically, which is more the way I like to do things, but graphically, x squared plus 1 is a parabola, and it's shifted up 1 unit. And when I'm asking when does it equal 0, I'm essentially asking you when does it cross the x-axis? And if you ask yourself that serious question, when does a parabola shifted up 1 unit, opening upward, intersect the x-axis? The answer is never. Okay, so there's no solution. These 2 graphs never cross each other, or if you try to solve algebraically. So there's no value that causes this to be undefined. So there's no reason to stop drawing it. Pick up your pencil. There's no holes. There's no factors that are removable from the top and the bottom, the numerator and denominator. And there is no jump. This is not a step function. This is not a piecewise function. This is also not even a square root function where my domain might only start after a certain point. So we have a polynomial. Polynomials are always going to have a domain of all real numbers. And I have a polynomial divided by a polynomial such that the bottom never equals 0. What does this tell me about my limits? This tells me that whatever I'm taking the limit of, whether I'm approaching a positive number, a negative number, or a number from a side, your answer is going to be found best by evaluating the function at the point you're approaching. So I have a quadratic for number 8, 2x squared minus 6x plus 1, right? If I just plug into this function, plug in 2, I'm going to get 2 times 2 squared minus 6 times 2 plus 1, and that's 8 minus 12 plus 1, and 8 take away 12 is -4, and -4 plus 1 is -3. Now, once I start evaluating a limit and actually taking a limit, you don't have to write limit anymore. But if you were just manipulating this, cleaning this up, doing work with it, you have to write limit every step of the way, okay? So the answer to this is -3. The next example, another quadratic, and this says the approach to from the left-hand side. Really, that's just there to kind of throw you off. It makes no difference, okay? You are still approaching 2. I promise you're approaching the same thing from both the left and the right. It's a quadratic function. So you still just plug in 2. So 2 squared, it's not -2, don't get messed up, plus 4 times 2 minus 3 is 4 plus 8, which is 12 minus 3. Final answer, 9. If I ever make a simple math mistake on here, I apologize, but I get a little distracted when I'm talking, making sure the camera stays focused. -1. Again, I'm going to go ahead and evaluate. I have nothing to worry about. If you put -1 squared is -1, well, then you have something to worry about. Filling in -1 squared plus 3 times -1 plus 2 over -1. And I know you might be able to do this in your head, but I'm just doing this for people that need to hear it said out loud or are doing it along with me and just want to practice their math. So 1 minus 3 plus 2 over. Now this might be where some people panicked because 1 take away 3 is -2 and -2 plus 2 is 0. But 0 on bottom, not a problem. If you notice on bottom you have 1 plus 1 and that is equal to 2. Couple rules. What are the rules that you need to know? The rules we need to know are as follows. When you have a 0 on top, we're going to write it right over here. If you have a 0 on top, it's okay. If you have a 0 on bottom, no. Okay, it's not a good thing for our limits. It tells us we probably have to graph or approach from one side or figure out if it's pointing at infinity or negative infinity. And then if you get 0 over 0, which kind of looks like our cute little division sign, that is called indeterminate form. And what that means is that we can probably divide out the problem and kind of spackle and fill in this hole and then take the limit of our repaired function. Okay? 0 on top is okay. So 0 over 2, that's okay. What does that mean? 0 divided by anything is 0. So what's the answer? 0. But all the times we get 0 on top, people assume you're going to get it on bottom because it happens so often. And they freak out. So this is probably something you should have in your notes, okay? And not just write these things down, but actually write more or less what I said and be able to make some decisions when you encounter each of these situations. In number 15, we're asked to find the limit when when x approaches 1. And for anybody who's done substantial practice with limits, you might look at a rational function and immediately think you have to factor and simplify, which is the case more often than not. However, you have to just keep up and pay attention. So even if you tried that first, because you didn't even want to test out if direct sub worked, you were just rushing along, for one thing, you have to write limit out front every step of the way until you actually take the limit. So can I factor this numerator? Looks like I would get an x minus 2 and an x plus 1 and an x minus 3 down there. Okay, so now looking at it in factored form, that doesn't do anything for me. So it would be even more upsetting if that were a 3 and a 2, which they like to do the one away on just a lot of college board assessments. They're a little sneaky and you think, oh, 2 times 1 is 3, or what multiplies to 3 and adds to 2. I don't know, people get all mixed up. So watch out for that. Here's a little better because you won't mess up so much, but there's definitely nothing that we can cross out. The fact of the matter is, for something like this, since we are only undefined at 3, direct substitution works for any other value that we're approaching. So really, I could just plug in 1. I could plug it in here, or I could plug it in here. Either way, I'm going to get the answer. 1 squared minus 1 minus 2 is -2, all over 1 minus 3 is -2, and -2 over -2 is +1. So if I just did direct substitution, so I'm just going to abbreviate with ds, I don't have to write limit when I'm taking the limit, so that's going to give me a 1 squared minus 1 minus 2 over 1 minus 3, -2 over -2 is equal to +1. So that is your answer. But of course, what am I going to do? In traditional me fashion, I'm going to go way overboard and talk about this problem to make sure we all have a really good grasp on topics that are going to come up. So if I look at my graph in, or my function rather, in expanded form, really like this, it's pretty quick and easy to identify a couple things. I could really identify my behavior a bit. I can identify my y-intercept, so the y things, and then I could really quickly identify my x-intercepts and my vertical asymptote. So when I'm looking at this example, and I really want to let's get my x stuff first. So which side do I look at for the x stuff? That one, okay. So what do I get for my x stuff? I get my x-intercepts. From the numerator, I get 2, and there's a cut through the x-axis at 2, and I get -1, and we're also going to cut through the x-axis at -1. So I have 2 x-intercepts. It's going to cut through right there. Now I want my vertical asymptote, and what decides my vertical asymptote? The denominator. Perfect, yes. So my denominator is x minus 3, which means I have a vertical asymptote at +3. It's undefined there. That is an infinite discontinuity. And in the future, in a few examples, and I mean like immediate future, like super near future, you're going to see that this vertical asymptote at x equals 3 is going to play a big role in a lot of our questions. Now, the next thing we are going to find are some of the things from the expanded side. So I'm going to look over here. If I plug in 0 for x, I get 2 over 3. 2 over 3 is my y-intercept. So if I go to my y-axis, 2/3, when I've filled in 0 for x, that's my y-intercept. And now the next thing I need end behavior. And behaviors, again, it's not this strict horizontal asymptote all the time. More often than not, it shouldn't even go through the middle. I often leave it blank in the middle when I draw. I try to focus on the ends because a horizontal asymptote is just the end behavior. If you were only taking a limit at infinity, which we do to find end behavior, we would ignore the minus x and minus 2. You could ignore the minus 3. You could really just focus on x squared over x, which reduces down to just x. If I fill in infinity into x, I get infinity. So as x goes out toward infinity, my y value also goes toward infinity, and that would be my limit. And again, it means it doesn't exist. And if I were approaching negative infinity, fill that in. So if I'm going to the left, my graph's going down. So really that tells me I'm going to have a slant asymptote. Now what if I want to find out exactly where my slant asymptote is? Well, we are going to basically divide. This is right now an improper fraction. We just did this when we were doing partial fraction decomposition. I'm going to divide this so I can see it more as a mixed number. Synthetic division works fine on this one, so I'm going to do synthetic in this case. So I have the 3, the opposite of number, basically I'm setting that equal to 0. So there's 3, and then my coefficients are 1, -1, and -2. I'm going to bring down that first number, 1. Bottom times box, I get 3. -1 and 3 is 2. Really, you're done. It's x plus 2. We're finished if you know that. But 2 times 3 is 6, and 4, that's my remainder. That means 3, 4 is a point on the graph if we were just using this 2-factor, okay, not actually dividing it. So if it was like finding a factor of a bigger polynomial. So what does this tell me? That tells me my quotient is x plus 2, and my remainder is 4 over x minus 3. This quotient right over here is sort of like the mixed number, and this is sort of like your improper fraction. If I did my end behavior here, that means I was analyzing what happens to my function as x approaches infinity. Well, this whole part's going to fall off. Infinity minus 3 is infinity, and 4 divided by infinity. Okay, you're going to get 4 slices of a pizza that you had cut into an infinite number of slices. So you get 4 out of an infinite amount. All right, or really, yeah, sure. So you get 4 pieces of that, and you're sharing it infinite ways. Well, you basically get nothing. This is 0, falls off. All we care about is the x plus 2. So x plus 2 is going to be my slant asymptote. And I could probably zoom out a little bit to kind of show a little bit more up high, but my asymptotes intersect over there, and that's my slant asymptote. And my vertical, I'm just going to extend a little bit past so you can see them crossing, and I will move this down for us to see it a little bit better. So I don't really need to see the synthetic division anymore. Okay, so here we have this so far. Now we said, here's my y-intercept, which you'll never basically kiss off of this, you know, like kiss the y-axis and come off, or you're never going to bounce off the y-axis. You're going to cut through it all the time, or it's not a function. Here we're definitely cutting through, and here we're cutting through. If you have had any experience with graphing rational functions, you should have a pretty good idea that this branch is going to look like this. Okay, you shouldn't default to using any graphing utility. Please don't get out a calculator. Please don't just put it in Desmos. You have to practice this if you want to be faster at finding limits. Okay, otherwise you're going to be really slow, and time is money. All right, if you want to get that AP Calc credit, if you want to pass college calc class, you got to just answer these questions quickly. So we cut through the axis at either of those points. Those are the only place we could cross the x-axis because those are the x-intercepts. There are no others. And then my vertical asymptote had a degree of 1, which also tells me that if this side's pointing down, then the other side of the asymptote is pointing up. And this is, again, just a sketch, but it's going to look something like that. Obviously not to scale, it's probably about equally far away, but again, I don't know how high this went. I just sketched it. When we get more into calculus, we find maxes and mins. We'll be able to figure out how high that is and how low that is, right? So here's this graph. So if I were approaching 3 from the left, the answer would be negative infinity. The limit doesn't exist, but you put negative infinity. If I were approaching 3 from the right, same idea, you put positive infinity as the answer. It does not mean the limit exists. If you were just approaching 3 in general, totally going 2 opposite directions, you would just put does not exist. But if you're approaching any point on a graph where there is not a discontinuity and the graph is continuous there and we could approach from both sides, then you're good to go. Just do some direct sub and call it a day. All right. Now, next example. The next example we have, I'm just going to move this out of the way, so hopefully you took your notes on it. The next example we have, if we filled in a 3 and just kind of went for it, 3 squared is 9, and 9 take away 4 is 5. Well, that tells me I have, if I show work, because maybe in the future you forget how you got your answer. So remember, you want to write this down. You're going to forget. You're going to learn a lot of stuff when you do calculus. So square root of 5 is the answer. You don't need to put a plus minus. The square root symbol was already there to start with. But I think it's really good to know what that function looks like, because not every number is going to be okay to plug in. So if this is the function you're taking the limit of, I can set it equal to y. Y equals x squared minus 4 all under a square root sign. What if I, and we've done this a dozen times before, okay, more than that, these are conic sections, okay? If I square both sides, I'm going to have y squared equals x squared minus 4. Now I'm going to rearrange it a little weird, but I'm going to bring 4 over there, and I'm going to bring the y squared over here. That's going to give me a positive 4 equals x squared minus y squared. And when we had conics, I could tell right now it's a hyperbola, if you have any practice with those, but I want to get that equal to 1, so I'm going to divide everything by 4. That will give me 1 equals x squared over 2 squared minus y squared over 2 squared. So I have a hyperbola. The center of the hyperbola is at the origin. I go to left and right to make the endpoints of my transverse axis. I go 2 units up and down to get the endpoints of my conjugate axis. You could draw the little box. You could draw your 2 asymptotes, which are going to both have a slope of 1 because your rise is under y. Your run, you run from your x. So rise over run is 2 over 2, which reduces down to 1 over 1 or 1. And you can graph that way. You would, if you don't find focus points, you can. However, this was a function. That means if you look up here, it was only the top half of the square root. So it goes from being this whole entire hyperbola to just being the top half of it when y is equal to the positive square root. So I could do a little sketch for us. I don't see why not. If you don't care, sure, fast forward. But honestly, I don't think any of this is going to harm you. If anything, it's going to help your ability. I need to go 2 units in each direction. The transverse axis is the one that really connects 2 things. If you think about a transversal, if you think about the transitive property, if you think of transit or transportation, so it connects the 2 things right there, right? These points are the ends of my conjugate. The conjugate has always been the other one. When we conjugate verbs in foreign language class, you keep the main beginning part of it and you change the ending. You rearrange it. If you have a conjugate of an expression, you keep the beginning part. You kind of change around how it finishes off. Here, you have the same idea, but you change around how it happens, the conjugate axis. So if you'd like to draw that, we said my asymptotes will have a slope of 1 that they pass through the origin, 0, 0. We can have those. But since it's the positive square root, it's only the top half. So I will have this little piece right over there and this little piece right over there. As x approaches 3, 1, 2, 3. As x approaches 3, over here, just on the edge of the screen, the y value is approaching the square root of 5. Can't really see it right there. So why was drawing this important? What else can happen? What if they asked us to approach 2 instead of 3? Here, you'll see there's a big chunk of space, this big gap in our graph. There's no domain, nothing in the domain between -2 and +2. Only those 2 numbers are included, but nothing in between them is included. So if the limit asks me to approach 2, while you do have graph over here, I don't have anything very, very close to it. So even though you could plug in 2 squared is 4, minus 4 is 0, square root of 0 is 0, it doesn't mean I could take the limit there because you can't approach it from both sides. So that's why drawing something like this is important, or knowing what your graphs look like is important. When you get pretty good at it, you're not going to have to sit there and try to draw this. You're going to understand that it's a conic section. Clearly, it is not x minus 2. It's not the square root function where you're just going to have the top half of the sideways parabola, although those come to be exactly the same way as these. Okay, which is also another reason why I like the idea of learning all the conics together and then learning the square roots, the y equals and the x equals all at once after, because I think it's a pretty cool concept. But this one's done. This one over here looks very similar. However, if you kind of do it in your head, once I have this equal to y, I square both sides, I bring this over. Do you know what graph this is? Think about it. Press pause if you don't want to hear the answer. This is going to be a semicircle. The radius is going to equal 3. They're asking us to approach 3 from the left. If this only said approach 3, not possible. But it says 3 from the left, totally doable. Do you need to graph it? No, you could just get the answer. All right. Over here, this one is pretty similar to actually that one, because you will have a minus sign when you try to bring this over by the y. It's just that my stretch on my horizontal and vertical directions will be different, so my dotted box over here will not be a square. It's going to be more rectangular, so you'll see that as well. Next, I have a couple of examples that are throwing in some properties of limits. People may have gotten these examples right, sort of just defaulting to common sense when they don't necessarily know the rules. So this says to you that the limit as x approaches c of f of x is equal to -1/2. So you don't know what the function is, and you don't really know what you're approaching, but they're telling you, hey, if this is true, and if this is true, for some other function as we approach c, we get 2/3. Find the limit as x approaches c of f of x times g of x. Well, the rule is the limit of the product of two functions is equal to the product of the two functions' limits. So really, all I have to do is multiply the two limits, and the 2's will cross out because they reduce down to 1, and I get -1/3. That is a property of a limit. Same idea, the sum or a difference, the limit of a sum or a difference is equal to the sum or the difference, depending on what you're doing, of those limits. So really all we have to do is find the limit for f of x when x approaches c, which is -1/2 minus 2/3, so -1/2 minus 2/3, common denominator 6, -3/6 minus 4/6 is -7/6, and we're done. Okay, you don't have to make up functions to try to make it work. Here, now it gets interesting. I shouldn't have to go way in depth. We should understand that this denominator factors to an x plus 2x minus 2. You should see that right away before you even start doing anything. If you try direct substitution, you're going to get 2/2 over 4 minus 4, which is 0/0, which is clearly indeterminate form. Okay, that's, I don't feel it right now, I guess. Indeterminate form, it looks like our little cartoony division sign. It tells me nothing. It tells me I could probably divide out a common factor, and guess what? I can. Pretty quick and easy, all right? Again, we should still have limit as x approaches 2 out front, x minus 2, and then x minus 2, x plus 2. And these reduce. I'm left with 1/, so I divided out the issue. That's the problem. That's what caused the 0 on the bottom. The 0 on the bottom is the no. Now that it's gone and I'm only left with this, all I really did is I spackled the hole shut. So when you have a hole in your wall, you spackle it shut. This is going to be the exact same function, except this one isn't broken. This is the same wall, but it doesn't have a hole in it anymore. Okay? This one had a hole in it. It looked exactly like this wall, but I didn't change any hole in it. Boom. Spackle, no longer a problem. Guess what works now? Direct substitution. Plug in the 2, and we get 1/2 plus 2. Final answer is 1/4. Done. Okay? The next example looks like the one that I went above and beyond for before with the slant asymptote. I talked about a few other things when I did examples like that as well. What else can we address? Well, now, sorry, I'm separating these for us. What are they asking us to approach? We're being, of course, now it's time. We're asked to approach -1 because that is going to be where my vertical asymptote is. Now, maybe it crosses out. Maybe it doesn't cross out. That's what we need to figure out. Is it a line with a hole in it, or is it a rational function with a slant asymptote of some sort? If you plug in -1 to the top, we're going to get -1 squared, which is 1, plus 5 is 6, minus 6 is 0. I'm going to get 0/0. In this case, it tells me that it's a removable discontinuity. I have 0/0 in indeterminate form, and I'm going to be able to factor and simplify. So the limit as x approaches -1, my numerator is x plus 1. When you get 0, when you plug in -1, that's also from the remainder theorem in Algebra 2. If you plug in -1 and get 0, that means x plus 1 is a factor. So if it was something a little harder to factor, maybe a cubic that you normally need rational root theorem for, well, it'll work out pretty nicely in your favor. And we're there. And I'm going to use a little spackle. And I'm left with just x minus 6. So this graph is a line of x minus 6 with a hole in it at -1. And this graph is just a line with no hole in it because somebody spackled the hole. That means now I could use direct sub, plug in -1. -1 minus 6, -7, and we're done. If I'm not going to do one of my full-blown graphs over here, but x minus 6 is 1, 2, 3, 4, 5, 6. Here's -6, and the slope is 1. So the graph looks like that. Well, before I fixed anything, I had a hole right there at -1, comma, the slope's 1, so at -1, comma, -7, right over there. Okay, I was undefined, so when I tried to plug in, it wasn't working out in my favor. So that spot right there is the ordered pair -1, comma, -7. And when I came along, and all I did was I factored and reduced down my rational expression, what that did, that swipe motion, was it came along and patched that up. And now you're able to evaluate, and that's where we got my output of -7. This function that I have written down is y equals the absolute value of x over x, which is actually equivalent to y equals x over the absolute value of x. It really doesn't matter which one we make absolute value. It's really going to give us the same outputs each and every time. Well, what is this new function? This is a really good opportunity to kind of point out that when it comes to things, even like the definition of continuity, usually people are like, well, why do we need a formal definition of continuity? I just know if a function is continuous or not. But the fact of the matter is you don't know every function. This right here is the quotient of two parent functions that you do know. We have the identity function, y equals x, and we have the absolute value function, absolute value of x, and we're dividing them. Now, what does this look like? If you want to say it looks like a V, you're wrong. If you want to say it looks like a line, a regular line, you're also wrong. Let's think about what happens. Now, what happens if you want to do it little kid style, when you plug in 1, when you plug in 2, when you plug in 3? If I plug in 1, don't just guess, okay? Don't be like 1 gives me 1, 2 gives me 2, 3 gives me 3, which I hear people say all the time. You do get 1 when you plug in 1. Now, what about when you plug in 2? Think about it. Come up with an answer. You get 1. What about 3? What about 4? If you plug in any positive number, you're going to get a number over itself. If you get a number over itself, that means you always get 1. If we're always getting 1, we're going to have a horizontal line. Again, keep in mind this is a function, so it's going to pass the vertical line test. But what happens when I plug in 0? 0 over 0, indeterminate form doesn't tell me anything. Okay, great. What about if I plug in a negative number? What do you get? Think about it before I write anything down. If you said you constantly get -1, then you're right, because you always have a number over its opposite, and again, you're still undefined right there. What kind of a discontinuity do we see in this new function? If this, you want to call it a new parent function, sure. The type of discontinuity we see, types we know, maybe you categorize them as removable and non-removable only, and that's fine. If you call it those two things, then this is going to be a non-removable discontinuity, because if it's removable, we can find the limit at the discontinuity, and I can't find the limit right there. It's non-removable, but non-removable has subcategories of jump discontinuities and infinite, and this is going to be right over here. This is a jump discontinuity when x is 0. Okay, so I want you guys to learn this as sort of a new parent function. You don't know this yet, but this is the derivative of the absolute value of x. It means nothing to you probably right now. If you're just reviewing functions, then sure, it probably makes a lot of sense if you actually pause and think about it. This is its derivative. Okay, now down here we're being asked to find the limit. What's the limit as x approaches 3? But what is this? What they did was they took really this function up here and they just applied a horizontal transformation. This really just moved this function in its entirety to the right 3 units. So these two open circles are going to be right there, and there's no reflection of any sort, no stretch, no nothing else. So I'm going to still have a jump discontinuity there. What does that tell you? As x approaches 3, what's the limit? Does not exist. But what are they going to ask us in a little bit? They're going to ask us to approach these numbers from the left. They're going to ask us to approach from the right. They're going to take this function, they're going to do reflections to it, they're going to do stretches to it, they're going to make it look very crazy, and you're going to have to do some manipulating before you find your final answer. Here we have a very classic limit example. If I try direct substitution, yet again, what happens, I'm going to go ahead and fill in 0 for x. That gives the square root of 0 plus 4 minus 2 over 0, which is a no. But I want to know more. Is it just the 0 on bottom, or is it the indeterminate form? If it's just 0 on bottom, there's an asymptote, a vertical asymptote, an infinite discontinuity. If it's on both places, it is indeterminate form, which tells me I can possibly fix this. All right, this problem is solvable. I can correct what's going on here. So that gives me 2 minus 2. Yep, showing above and beyond all the work, but there it is, 0 over 0. Now I mentioned in the function video that whatever causes this 0 on bottom, and I colored it this purple color, this is your little devil emoji from your emojis on your phone, right? He's got to go. He's evil. He's causing all the trouble. He's the no. He's the O in no. He puts the O in no. We got to get rid of it. But that 0 over 0 division symbol look reminds me that this x could somehow end up getting removed or kind of spackled out of here. But right now, the only x it could potentially reduce with is right there inside the radical. This expression, or this function over here, has a rationalized denominator. By rationalizing the numerator, I will end up with a radical on bottom, sure, not a big deal, but it's going to help us rewrite the numerator and help us rewrite the expression that it might end up being a bit more solvable. If you remember geometry, algebra 2, anything in pre-calc, you should know how to rationalize this numerator. Rationalize means to get rid of the thing that is irrational. So when we rationalize a denominator, we make it, we remove the irrational thing. Okay, so we got rid of that irrational expression. But we're going to rationalize our numerator right now. How do we do that? You cannot just square it, okay? That would change its value. And you cannot just multiply by the square root of x plus 4. I mean, you can try, but you're going to see it's going to get you nowhere. You should know, if you've made it this far, without any issue, you should be able to tell me that you would multiply by the conjugate. And it would be a little nicer if you said it by its name and you didn't say, oh, multiply by square root of x. Oh, I guess I'll put the one with the plus in front. You multiply the square root of x plus 2 over the square root of x plus 4 plus 2. Sure, you're right, but let's call things by their name. That's the conjugate. So I'm multiplying on top and bottom by the same thing, which means I'm really multiplying by 1. And what was originally there, I don't know why I wrote it in front. I messed up writing. But square root of x plus 4 minus 2. And here is my little devil x. Could I just go ahead and reduce this? Sure, you can. But that would completely defeat the purpose because we're the ones who put it there. Okay? We put it there on purpose. We need to see what happens. So let's go over here. If I expand that numerator, if I multiply two conjugates, the outer and inner expressions will cancel out with each other. So the limit as x approaches 0 of radical x plus 4 times radical x plus 4 is just x plus 4. Outer and inner are going to eliminate, and I'm going to have minus 4 right there. When we spend a really long time doing trig identities, right, we basically learned how to algebra from trig identities. We got much better at our algebra. We knew not to always distribute when you were multiplying by conjugates. You really only distribute when they're worth mixing those two ingredients. Like it's with its conjugate totally worth it. Here, not worth it. You want to cancel out the x, it's the devil, so don't distribute it and give more devil to all the expression. So I'm going to leave that x out front. I'm just going to rewrite it so it's square root of x plus 4 plus 2. There we go. Always make sure your square root symbols, make sure your division symbols are all the right length, that you're not getting sloppy with them, okay? What is going to happen next? Well, in the numerator, plus 4 and minus 4, when you have adding and subtracting the same number, they cancel out. Then I'm left with an x in the numerator plus nothing, just x over x, and that's going to reduce. Notice my word choice. Okay, I say reduce, I say cancel, I'm using the right word. Because really it's just equal to 1. And then that means, now that the devil is gone, okay, we got rid of it, that we can evaluate the limit. Okay, we can plug in. I started writing limit, so I guess I'll write it over simplified. Limit as x approaches 0 of, there's a 1 on top, and we're just left with radical x plus 4 plus 2. Alright, fill in 0 now. Square root of 4 is 2. 2 plus 2 is 4. 1 over 4, 1/4. And we got the answer. Okay, so for these, every time you see an example like this, I promise you that this will work. If it's not working, it's not the problem. It's probably you. Check your work. Don't make assumptions, right? One of the 4 agreements, if you've read the book, the 4 agreements, don't assume. Do not assume, do not make assumptions. Make sure you know for sure before you do anything, okay? So you evaluate it, you plug it in, you check your work, you make sure you're not guessing what the answer will be, you're actually doing the work, okay? And that's 2 plus 2 is 4. Here I've jumped to number 46 and I brought back the graph from a couple examples ago. So this new parent function graph, and over here we're asked to deal with it when it has x minus 2 filled in for both x's, okay? That moved this entire graph, because it's filled in both x values, it moves the entire graph to the right 2 units. So where are they going to ask me to find the limit? You guessed it, at 2. But it has a plus sign. So what does that tell me? It wants me to find the limit as we approach 2 from the right. From coming from the right side, think about the picture. What's that limit going to be? If you said 1, you are correct. the other thing about these is, if you're careful, what could you do? I never do it, but what could you do is you can plug in that number, or I'm sorry, plug in any number to the appropriate side of that number, and you'll get your answer. Okay, so 2 from the right, so I could plug in 3. 3 minus 1 over 3 minus 1, they're both positive 1. 1 over 1 is 1. Okay, I just worry that people are going to make silly mistakes, so just be careful with that. Just to clarify, I promise the whole multiply by the conjugate thing will work on these examples. All right, it should have absolutely worked on the ones after that one I went over. If it didn't, keep in mind, what is the devil? For one of the examples a little earlier, the little purple devil was going to be the expression x minus 1. Okay, in this case, what's the problem? Really, it's the whole entire denominator, right? If I plug 0 in here, I'm going to get the square root of 4 plus 2. I'm sorry, square root of 4 minus 2, which is 2 minus 2, which is 0. So this whole thing is the problem, which means I sort of need to get this on top. So you might need to multiply by the conjugate. It's going to clean up the whole bottom. You're going to get a new, you're going to rationalize your denominator. You're going to have a irrational numerator. That's what I meant by get this on top, and it'll work. Okay, so please remember, just persevere, follow through. And it might look funny because you see the square root of 3, but really that other example had a 2 here and a 4 on the inside. Even actually this one does. But isn't 2 the square root of 4? Couldn't I just have scribbled out 2 and written square root of 4? So it just happens to be a perfect square, so we don't end up with a radical there. There's really places where all this stuff has come from. So you can do the same thing for these examples. I'm not going to finish them, but I'm just kind of trying to give you a little pep talk before you go for it. Here I have 53, 54, and 55, and I'm actually going to start off with number 54. I'm going to go a little bit out of order because I feel like it might shed a little bit better light on the situation. So here I have a classic square root function, and it's shifted to the right 1 unit. That puts a point right over here. If you know your graphs really well, you should have that understood. And then I know the shape is that of a sideways parabola, top half. So I know I'm going to go up 1 over 1, and then I'm going to go up 1 and move over 1, 2, 3, a pattern that we always use in my classroom, right, to graph these functions. So I have this right over here. Now it's asking me to find the limit, as x approaches 1 from the right. So is that okay? Sure, I can approach 1 from the right. My answer is 0. So the answer is 0 for this. Always be careful when you are writing 0 as an answer. I feel like it gets lost on people's papers when they have a lot of stuff going on. The answer is 0, but if it did say to just approach 1, you would not be able to do that because you can't approach 1 from this side, okay? So make sure the limits are written out correctly. Here, if I plug in 2, 2 times 2 is 4 minus 1 is 3. The square root of 3 is the answer for this example. But how do you know where the issues lie? Really, if you get 0 for a case like this, that's where you're going to, it's going to raise a red flag, okay? If I wanted to graph this just to make sure that everything is going smoothly, is this like a flag, right? Something like that? Okay, there's my red flag. And that's being raised for that example, and that's what made us check right there. Now, here, I'm going to do a little rearranging, a little rewriting. If I factor out this 2 over here, I'm going to be left with a 1/2 in there because I need to see it, and this is kind of like a vertex form or transformation form. Move to the right 1/2. The 2 inside of the square root is actually a horizontal compression. So instead of going up 1 over 1, up 1 over 3, I'm going to go up 1 over a half. I'm going to go up 1 over, instead of 3, I'm going to go 1 1/2. Pretty sure I went over examples like this in the function packet. Now, if I'm being asked to find the limit at 2, well, should it raise a red flag? Here's 2. We're totally fine. Do you see you're not in the danger zone? But where, and then, well, actually, that's that point. We're coming from both sides of that, so we're a little next to there. Okay, so we're not at that dot. We're a little bit lower. That's the rad 3. So we're fine. We have no problem. But where is the danger zone? Right there. Because you don't have that other end. It's sort of the beginning or the end of your domain. So you got to watch out. For this example, once again, I brought back the graph paper sticky with the parent function on it. Here again, we have a transformation of this function. How can I make this look sort of more like a vertex form, like a transformation form? Well, if it's an absolute value, you can factor out a positive number, so I can factor out an 8. What does that leave inside the absolute value bars? That leaves an x minus 7 on the bottom, or in the denominator. If I try to rearrange it a little bit, sure, that's a negative x and a positive 7, but that doesn't really follow those rules we saw happening before. It seemed that whatever was in here was going to match whatever's underneath. If I factor out a negative, if you factor out a negative or a -1, I do get that expression. So I'm going to take that negative symbol, I'm going to give it to that 8 right there, and I have x minus 7. So what did this do to my graph? I have a vertical reflection. So these two lines pointing in opposite directions are going to flip over the x-axis. So I'm going to have one over here on bottom, and I have another one up here. The 8 is a vertical stretch of 8. So instead of being at 1 and -1, well, now they're at 8 and -8, and it's to the right 7. Well, if it's to the right 7, where are they asking for the limit? Of course, as we approach 7, but from the left. So remember, what does this graph look like? Again, I sketch them out all the time. Here I have my graph, not to scale, but there's 7. And I have up here at 8 and down here at -8. Again, not totally to scale. There was a reflection, so this side is pointing that way, and this side's pointing that way. So I'm approaching 7 from the left. What is that? Not 1. Be careful. It should be 8. I didn't label it, just did a little sketch. So it's positive 8, okay? So what's happening is somewhere over here, that's 8, and somewhere down here, it's -8. I guess I could cut this. Okay? Not the most beautiful graph, but it does help. And what was the other way to do this? I said you could pick any point to that side. So take any point to the left of 7, fill that in for x, any x value, evaluate, and just be careful, and you should also get 8 no matter what, even without rearranging this and looking at it as a new graph. You've definitely been prepared for examples like this if you watched the video with the function examples, the function set. If you didn't, please go back and watch it, okay? I spent a really long time really dissecting everything with this setup. Don't try to be a hero. If you're confused, you shouldn't be if you're starting calculus, but if you are, you should really definitely go back and watch the function review, okay? It's a really big deal. So you pause this, go to the other video, and come back when you're ready. If you are ready, just to go over this quickly, we have the limit as delta x, which is the change in x, as delta x approaches 0. So if you have a change of x, okay, it could be anything. The change in x could be 5, the change in x could be 1, but we want this change in x to get closer and closer to 0. So really these two x values are actually going to get much, much closer together that we're talking about. And this will all become very relevant in a bit. I'm going to use Pascal's triangle to expand that and distribute the 2 at the same time, and I'm going to distribute the negative. So that gets 2x squared plus 4x delta x plus 2 delta x squared. That's just that quantity squared so far. Still got a bit to go. Plus 1 minus 2x squared minus 1 all over delta x devil. Little devil emoji, I promise. So if you work it all out, play around with it, you've learned that that is our little devil. If you go to plug in 0 for delta x now, you will get 0 over 0. We don't want that, so we got to fix the problem. If you carefully analyze the top, you'll see, and this always happens, and I already discussed it, we get rid of a whole bunch of stuff. The stuff that's left, everybody has something in common that gets us to our next step. Again, go back and watch the old video if you're confused. Don't be a weenie. Don't try to be a hero. Go ahead and watch it. If you're not ready, you're not ready. And really that's over 1, because guess who we got rid of? The devil. And guess what we could do now? Direct substitution. So if I fill in 0 for delta x, this falls off. Who needs to write over 1? Final answer is 4x. So in these examples, you will get an x in them. You don't know what this really is yet, or you do because you have me as a teacher and I explained this to you a million times already. It is actually the limit definition of a derivative being applied to this function 2x squared plus 1. And what you found is the change in y with 2 different inputs for x over the change in x. As that change in x gets closer and closer to 0, which I did explain and I will explain later. And we worked it all out and got 4x. So that's the derivative right there. It's in terms of x because the slope of a quadratic depends on the x value that we're looking at the function at. Okay, if we have 2x squared plus 1, it's going to be a pretty narrow parabola, shifted up 1 unit. The slope here, the slope there, the slope there, the slope there, the slope here. It's going to vary, and it varies and it depends on x. So we should have an x in this thing to help get us the slope. Alright, so that's in your future. This was a little healthy foreshadowing.